at the same university. His research focuses primarily on utilizing concepts of symmetry through the lens of group and representation theories to develop new quantum chemical formulations and computational methods. He is particularly interested in understanding the electronic structure of challenging systems involving various degrees of degeneracy, especially those containing heavy elements with d and f electrons in highly symmetrical environments. He also has experience developing and running quantum chemical softwares in various programming languages such as Python, C++, and Rust throughout his research work. Ladies and gentlemen, with a clap ovation, let's welcome Dr. Bang.
Well, thank you very much for the introduction. Can I get my slides on the screen, please? Thank you. Sorry. It's on the stream. Oh, did I leave? Okay, I'll do that right now, yeah. So just one more. I see, that's right, yeah. Is the Aodi okay, I think it is connected now. That might be bad. I've joined the AODI again. So which one is the AODI? The Starlink, yes. Starlink is doing now? Simply lower now. Oh, okay. Yeah. So the Starlink is just showing that it's completing. I don't know, but it's working now, so I will. That should be fine, I hope. Okay, this is for intro, so yeah. Yeah, so I'm trying to connect to that now. Connect that. Okay. Not starting. Not starting. That's an option, but I can really hold it for me. I can actually do this. I can host. hear me at the back? Okay. Yeah, right, okay. So, sorry about that. So what did we learn yesterday? I think someone mentioned that we learned quite a bit by NMR. But what else did we learn yesterday? Anyone? Just shout. I mean, it doesn't matter. Just shout for the crowd. So what did we learn yesterday? Oh, it's coming. Yeah. Right, so what did we learn yesterday then? Anyone? Or shall I call a random person? Okay, I'm going to call a random person. Can you tell me what you learned yesterday? Yes. Yes. So what did we learn yesterday? Or what did you learn yesterday, rather?
Good day, everyone. My name is Fabian, and I learned a lot yesterday. I learned the principles of spectroscopy, the different methods of spectroscopy, their various forms, and how they are used to analyze some specific samples. Thank you very much.
Okay, thank you very much. So yesterday you learned a lot about spectroscopy and spectrometry. So they are essentially tools that chemists use to understand chemical properties of substances, of compounds that we synthesize in the lab, to understand broad chemical reactions. We want to understand whether a chemical reaction has gone to completion, whether a chemical reaction has produced the product that we want to produce, or whether the product that it has produced has all the properties that we're expecting. So we use a lot of analytical techniques to help us probe chemical properties. So that's on experimental level. And you've seen examples of NMR spectra, of IR spectra, of some mass spectra as well. And they were quite simple yesterday. I mean, because the molecules that you're looking at were fairly small, and the spectra that you saw yesterday were, fairly easy. It can be understood quite easily. But when you get to larger systems, you start to produce very complicated spectra. You start to have very complex chemical properties, electronic properties, and magnetic properties. So how do we actually go about understanding them? Well, the one way that we can do that is to do more analysis. And because the more data you have, the more information you're going to be able to gather to sort of piece together all the puzzles, all the pieces of the puzzle to give you a bigger picture of the system that you're looking at. But there's another way that you can also use to understand chemical properties, and that is to do theoretical modeling. And that is essentially what we're going to do today. From the theoretical perspective, you can see, you can use fundamental theories, for example, quantum mechanics or classical mechanics even, to predict behaviors that molecules have. Because from your theoretical understanding, you can get some sort of prediction, and then you can try to correlate prediction that you get from theory with experimental results. And you can use your theory to complement the experimental data that you have to try to rationalize the parts of the experimental spectra that could be very hard to understand if you just look at them by eye, for example. So today we're going to do that. So in the first session, we're going to have Dr. Alex Tom, who will give you an introduction to quantum chemistry, or to computational chemistry in general, actually. So he's going to speak about, how the field of computational chemistry has come about, what sort of things are involved in computational chemistry, and what sort of things you can do with computational chemistry to help you either understand your experimental results or to develop further chemical knowledge. And then there will be a hands-on workshop where I'll show you, some ways that you can actually use these theories to run calculations and to get useful predictions that you can then use to look at your experimental results. And finally, we have my colleague Ross from Nottingham. He will be calling in and he will be giving you another tutorial on how to use molecular dynamics. So my tutorial is going to be very much based on the quantum part of computational chemistry, and Ross's tutorial will be based on the molecular dynamics part of quantum chemistry. So that's going to be a lot more classical, but it is going to enable you to model much larger systems, such as drug interaction and so on. And that could be very useful for a lot of you in the audience who are sort of looking at drug discovery or who are trying to understand very large biomolecules and so on. So I think with that, let's enjoy our theoretical day today. And I think first to speak will be Dr. Alex Tom, and he will tell you a little bit of an introduction about computational chemistry. So enjoy that.
Could I have some slides up, please? Thank you. Thank you very much, Bang. We have a shorter amount of time than we would have liked today, but I'm going to, this morning, give you an introduction to the concepts you need to be able to understand and do computational chemistry well. Computers are amazing things, but there is a saying, garbage in, garbage out, and if you can use computers to produce any result you'd like. To do proper science, you need to understand what you're doing in order to produce numbers that make sense in a context of chemistry. It's coming up soon. So I'm going to try and keep the amount of maths to a minimum because we are condensing a lot of course into a short amount of time, and give you concepts which build on concepts, which build on concepts to enable you to understand the things you need to get in out of the workshop today. Can I ask about slides? There should be one called ITCC, I think. So in the meantime, I'm going to give you a bit of a background of history. If you've got some slides, I can talk through it, but I'll work without the slides for now. So physics tells us everything we need to know in chemistry. The background, the physicists worked out in the early 1920s, and in principle, we can calculate the entire of chemistry without doing any experiment at all. This was very appealing to me because as an undergraduate, I spent a lot of time in the labs, and it was not always successful in my lab career, so I became a theoretical chemist in order to be able to do chemistry without having to spend many hours of lab work. Why would we care about that? Well, labs are very time-consuming, very expensive, and being able to do chemistry with as few resources as possible is very helpful. So ideally, we'll be able to take you through how you can predict things chemically without many resources. So starting from the 1920s, the idea of a chemical bond came about from theoreticians. The bonds Nick showed you yesterday when you were looking at breaking bonds in mass spectrometry are an idea called valence bond theory. That started very early on and predicted some very simple molecules, diatomics, and how to break them. Most chemistry involves bonds, but most chemistry involves very large molecules. And so to predict properties of larger molecules, they moved into the late 1920s into a period where they looked at something called molecular orbital theory. Now, again, Nick talked about molecular orbitals. I'm hoping the idea of molecular orbitals is familiar. They are where we put electrons in a molecule. And we're going to build on that in this short talk. Following on from the molecular orbitals, this was before any form of electronic computers. So any form of calculations were done by a hand-cranked mechanical computer. and they were able to calculate small molecules up to the 1950s. Then computers became more readily available, and they were able to start calculating on computers the size of this room. Maybe water is an example that happened in the 1950s. Computers have got so much better. This computer here is 1 million times more powerful than the computer that took a room in the 1950s. And so we can do very powerful calculations on relatively small computers. The problem with computational chemistry is initially the computers were small and the calculations were difficult. So people started making approximations, and to get anywhere in this field, you need to make approximations. The first approximations were starting to look at, instead of electrons in a molecule, discretizing that into atoms and springs. Nick talked about a model of vibrational spectroscopy yesterday, where you can imagine a molecule as a set of atoms and springs. This simplification is called molecular mechanics. It is a simple but incredibly effective approach to simulating chemistry. It is not always 100% accurate, but it enables you to look at the vibrations of molecules, for example, and how they bounce off each other, but it is not able to look at how bonds are formed and broken. In order to do that, you need electrons. So the best theory involves looking at the Schrödinger equation. We will get to that, and I'll show you some basics of that in time. Later on, the simpler theories involve atoms and molecules interacting through classical physics. If your systems are very large, if you have a small cell of water that has 1 million molecules in it, that is too large to calculate, even imagining molecules doing Newtonian mechanics. And so instead, we work on a far larger level, where instead of molecules, we take a chunk, for example, of DNA and regard an entire base or base pair as a chunk of something. And you can build up very complicated structures like polymers, DNA, proteins by a process called coarse graining. Okay, yeah. Okay. Oh, no, it's fine. This is, yeah. Okay, some slides are coming at some point, but I'm giving you a bit more background here on this. So the coarse graining approach is what you do if you do not have enough computer power to simulate everything atomistically. In the department in chemistry, for example, we have a very large theoretical research group, and it involves people like me who look at quantum mechanics of electrons and small molecules, through to people looking at relatively large molecules interacting with other molecules, up to people looking at molecules involving proteins interacting, and then the world of coarse graining, where instead of having a molecular system with atomistic detail, you just imagine a polymer as a floppy string, and you can do the calculations on that explicitly using parameterized models. So I built up a structure from the very accurate quantum mechanics at the bottom through some force fields, molecular mechanics, and then up to a coarse-grained approach where you've added parameters. All of these top-scale parts of chemistry must be founded either on experiment or other theoretical calculations that are accurate. It's possible to build theories where you don't know anything about how things interact, but it doesn't tell you anything about the real world. So part of the process of building up quantum chemistry into molecular dynamics and the protein molecule interactions was being able to start with the small calculations, which are very accurate, and parameterize them, take a lot of information, put it into smaller information, and build up larger models in that respect. Okay, so we're going to, later on, I'm going to give you some examples of how that approach can be used very generally, and I will talk about machine learning and artificial intelligence in the later session of the day, because that is where that part of chemistry has ended up. But in the earlier part today, I'm going to talk about how you build the very accurate quantum mechanical calculations from which you can then build on. Now, Bang has sent some, we've got some software that's hopefully circulating around, and some calculations will be going on that later on. I'm going to give you the snapshots of what we need in that case. So, if my computer works. Right. Let me start. Aha, perfect. Ah. Right, okay, some slides are coming up. So, Ben, can you go on to the one electron Hamiltonian, I think? Okay. Under MOs. Yeah. Oh. Okay, so I'm going to first introduce where molecular orbitals come from. Now, the molecular orbital is, I would say, the single most successful concept that has come out of theoretical chemistry. So successful that people can use the idea of orbitals to do organic chemistry without ever understanding where orbitals come from. So, molecular orbital, you will have seen if you've done some organic chemistry or some reaction mechanisms, is a place where electrons reside in a molecule. They, in a, for example, SN2 reaction, electrons will start in a molecular orbital, an occupied molecular orbital, and move to an unoccupied molecular orbital of an acceptor. But what exactly are these orbitals, and how do we calculate them? In principle, we can do a calculation which enables us to... Oh, okay. Is this quick? Is that you? Okay. Right, fine. We have some slides now. So, the key part of theoretical physics that comes into chemistry is something called the Hamiltonian. You can think of electrons as sitting in wave functions, and I'm not going to worry about physical interpretations or philosophical interpretations of wave functions. You could think of a wave function as a way of putting electrons into a molecule. And the universe does its best to minimize the energy of that, and out comes what would be called a wave function. I'm going to call that psi at some point. In order to build a wave function, we would like to put individual electrons in a molecule. And so we're going to solve an approximate equation called the one electron Hamiltonian, which I've denoted maybe on here. Okay, little h. So how do we go about evaluating what the energies of an orbital are? Okay, so the Hamiltonian for a whole molecular system is very complicated. We're going to make approximations so we can imagine electrons as being independent. This is where we take the Hamiltonian for a molecule, which tells us the energy, and produce a set of Hamiltonians for individual electrons, which tell us the energy of an electron. And I'm not going to go in the maths behind how you do that approximation, but important parts of that are the kinetic energy. That's called T. That, for an electron, is to do with how delocalized an electron is. So a very delocalized electron will have a very low kinetic energy, and a very localized electron will have a higher kinetic energy. The other components of electron energies are the nuclei. Nuclei are positive, electrons are negative, the electrons are attracted to the nuclei, and remaining, this is a classical term, electrons hate each other. They are both they're all negatively charged and they repel each other. So there is a repulsive interaction between electrons. All three of those are balanced together in the total energy of an electron. And when you're doing a calculation, you would like to find the ground state, the lowest energy of a molecule, and we find that by finding the lowest energy that any individual electron can have and build up a set of molecular orbitals of increasing energy. This is an approximation. Electrons ideally would see each other and respond to each other, but in this case, electrons will interact with an average field of other electrons. So all of the pictures you will have seen in molecular orbitals have involved electrons interacting with their average field of other electrons, and this is called a mean field approach. Okay, this is also sometimes called self-consistent field. They're almost interchangeable in this case. Yeah. Okay, so what is a molecular orbital? A molecular orbital is built up from orbitals on individual atoms. Those are called atomic orbitals. And to find out the composition of an individual molecular orbital, you need to solve a complicated equation which is now happily implemented in every single piece of quantum chemistry software. So you don't need to do it yourself. But importantly, that equation produces an orbital and an energy. And so for every single molecular orbital you have, you can label it with an energy. We can say some electrons are low energy, some electrons are higher energy. You might then ask, how do I work out what the total energy of a molecule is? Can I just add up the contributions from all my individual electrons? Well, the answer is no. Surprisingly, because of the approximations we've made, electrons interacting with the average of other electrons, if you add up their individual energies, that doesn't give you a total energy which is meaningful. So in looking at molecular orbitals, you have to be very careful interpreting energies. So energy changes of single electrons are generally very good, but total energies, adding up all of those energies, are not good. And I'm going to come at how we solve that problem later on. Okay. So to build up our molecular orbitals, we needed some atomic orbitals. And one of the things you need to do that is have some atomic orbitals at hand. If I want to build a tower out of Lego, I need Lego blocks that fit together appropriately for that tower. When we do computational chemistry, those Lego blocks are called the basis set, and they are a basis set of atomic orbitals. There is a huge range of work that 60, 70 years of people have done to find the appropriate Lego blocks, the appropriate basis functions for building your molecule. And they're all available free on something called the Basis Set Exchange. All of your software that you will use has got all of these in it already. But I'll give you an example of one such basis set. This is called 631G star, and we'll go through a bit of what that means later. But for a carbon atom, it means every single electron on that atom has to be at least represented by some orbitals, and then additional orbitals have other functions. So in this example, the first left dot you can see corresponds to a 1s orbital for the carbon atom, and we're going to represent that with a single orbital, atomic orbital. Next comes, in carbon, 2s and 2p orbitals. The next block of 4 by 2 corresponds to one set of 2p orbitals and a 2s orbital, and another 3s and 3p orbital. Those are used to describe the valence electrons in a molecule. And then finally, I've got 5 d orbitals. In this case, those are being used to describe changes in the atomic density through polarization. So in the code 631G star, the 6 corresponds to the core 1s orbital, The 3-1 corresponds to two different sets of valence orbitals, and because we're looking at bonding, we want to give orbitals in the valence space some flexibility to lower the energy as much as possible. And the star corresponds to polarization, where the electron density can polarize by electronegative atoms, for example. And to change something that looks like a P function, you add D functions to it to enable it to distort, for example, at a molecule like H. Basis sets can seem very confusing, but you can rank them in a bit of a hierarchy from small to big. The more functions you put in, the better your energy will be, up to a limit of how good the type of calculation is. I'm going to talk about the type of calculation very shortly, but in general, you will have a dial you can turn on your basis set. You can make it bigger and bigger. Making it slightly bigger is good. If your results don't change, you can stop. You don't need to keep on turning that dial up until you get to a fully converged energy. Okay. So, the first bits of quantum chemistry, in order to solve for the molecular orbitals, they did not have big computers. And so they made a lot of approximations, and these are called semi-empirical methods. One we teach in Cambridge as a really good example of how to think about how orbitals interact and build bonds is called Huckel theory, which only describes formally the p electrons in an aromatic pi system. But from that, you can extend those descriptions and start building up other descriptions of more and more orbitals, and these approaches were called originally NDO, neglected differential overlap. There are lots of acronyms in chemistry. You don't need to worry about most of them. That is a very old-fashioned method, but it will sometimes appear when you're reading papers. But most importantly, the one electron Hamiltonian approach has been turned into something called a tight binding approach. And very recently, something called extended tight binding, XTB, has parameterized the orbitals and the Hamiltonian so that you can get very, very good bond breaking out of very, very cheap calculations. So if you need to do approximate calculations on large systems, this is an approximate approach where each electron sits in an orbital and feels an average field of other electrons, but you can break bonds in this approach. This is usually a very good starting point if you haven't got a lot of computer power. It will generate you molecular orbitals, and you can think about what your electrons are doing in a molecule. But you should not trust the energies of this. You can look at the orbitals, you can look at approximate things, but you should not trust the energies to a high level. You must do better calculations. And the thing I'd like to emphasize in all of this is that as you do a calculation, you should always consider what is the next calculation I can do that is better, that tells me my result was correct. So, one of the most important concepts in computational chemistry is that orbitals don't really exist. Orbitals are a way of building wave functions to do chemistry. The simplest possible wave function you can build is a many electron wave function, which is a very complicated function. If there are n electrons in a system, there are 3n coordinates of electrons, and it is your wave function psi is a very complicated function. The simplest way of building that is to put one electron in each orbital to build that up. That is called a Slater determinant. You don't really need to worry what's going on in a Slater determinant, but just appreciate that it is a way of creating an electron configuration built up of electrons in specific orbitals. The simplest approximation that gives you a total energy and a wave function for your system is called Hartree-Fock theory. This is where we build up a wave function out of orbitals and we optimize those orbitals to give the lower but they have an extra quantum mechanical effect called exchange. Now, exchange is a really important feature in quantum mechanics because it stabilizes systems with unpaired electrons of the same spin. And so if you don't have exchange in your system, you will not necessarily represent different spin states of your molecule correctly. So Hartree-Fock theory introduces exchange and enables you to build wave functions which have correct total energies. Out of Hartree-Fock theory, you still get molecular orbitals. So most of the molecular orbitals you may have seen might have come from a Hartree-Fock calculation. It has the same problems as other one-electron theories in that you can't just add up energies of the orbitals. You should look at the total energy of a molecule, not the sum of the orbital energies. So, can we just stop there? We can build a simple model of a wave function by occupying 2 electrons in each orbital, for example. Unfortunately, it is not good enough to do quantitative calculations. Why is that? Well, electrons are quantum mechanical, and they repel each other. In Hartree-Fock theory, the mean field theory, electrons only see an average, smeared out version of the rest of the electrons. And this doesn't allow electrons to repel each other individually. What we should get in a true wave function is something called correlation, where if there's an electron here, other electrons will be further away. Electrons don't like being close to each other. So in the true wave function, we should get, and the top picture on the right-hand side shows 3 lines. There's a straight line, which corresponds to electrons that don't see each other. They just see an average field of each other. The red line corresponds to electrons of different spins. And when 2 electrons of different spins come to the same place, there is what is called a cusp. You can see this where there's a pointy bit in the wave function. Those cusps are really important in describing a wave function and then producing the correct energy. If you don't have them, your energies are too high because the electrons don't repel each other. When you have 2 electrons of the same spin, you get the black line, and that has a cusp which goes to 0. So when a wave function is 0, there is no probability of 2 electrons being in the same place. That's a consequence of something called the Pauli exclusion principle, and that's a principle that enables me to stand on this podium and not fall through it because my electrons don't want to be in the same place as the electrons below. Okay, so electron correlation gives you the right wave function, or can give you the right wave function, and electrons avoiding each other at short range is called dynamic correlation. If you are, for example, a person moving through a very large market of people, it's very difficult to move through that if everyone doesn't know each other's existence. You keep on bumping into people. But if people can see each other, they move out of your way and you can move through that easily. That will be a local correlation effect. Another form of correlation is called static correlation and comes when you break bonds apart. So there's an example here on the hand side at the bottom. When you pull apart the hydrogen molecule, H2, this is my favorite molecule because it's the simplest possible molecule you can make and yet is wonderfully rich and complicated. The black curve is the exact curve and it shows the energy as you pull apart the molecule as the bond length, H2. The red curve is what you get if you do Hartree-Fock theory. Hartree-Fock theory will put 2 electrons in the same orbital and pull the molecule apart. But even at 5 miles between the 2 atoms, that's still a molecule, and it still puts both electrons in the same orbital, and therefore has put 2 half electrons on each atom. Now that's not the correct way to pull apart a hydrogen molecule, and that gives you an energy that is too high. What you want when you pull apart a bond is the electrons on one part to be on that part, and the electrons on the other half to be on their half. You don't want them split over the two molecules. And that is another electron correlation effect. Electrons on fragment A need to know not to be on fragment B. And so electron correlation is really important when you're pulling apart bonds. So in Hartree-Fock theory, there are ways of getting around this. A lot of chemistry doesn't take a molecule and fragment it into individual atoms, but if you do it, you'll find that the atoms you make have unpaired electrons. So if I take the hydrogen molecule, HH, and put it into two hydrogen atoms, each of those atoms will have a single unpaired electron. If you allow your electrons to have different spins in different places, you can put one upspin electron on one atom and one downspin electron on the other atom, and you can actually dissociate hydrogen correctly. You can do this for much larger bonds as well. So the nitrogen molecule has a triple bond. You can allow it to dissociate to 3 upspin electrons and 3 downspin electrons. This is an approach called unrestricted Hartree-Fock theory, and the picture on the top right shows the orbitals in that case. You get an orbital which is distorted on one side and a different spin orbital distorted on the other. If you are treating systems where there are unpaired electrons, there are ways of doing this. Unrestricted Hartree-Fock is one way of doing it. You can also force electrons to be in the same orbitals, paired at lower energy, and then unpaired at higher energy. If you can see on the right-hand side, I've got an example of that, where I've got 2 doubly paired orbitals with 2 electrons, and then 2 single occupied orbitals, both upspin. That would be called a restricted open shell calculation. Those calculations produce the right sort of dissociation, and if you are looking at magnetic properties, produce spin states of a molecule that are correct. However, because we have restricted those orbitals, we have not got the lowest possible energy, and therefore you can get lower energies by something called unrestricted calculations, but there are problems with those because they produce sometimes bad spin states, so you have to be very careful. So how do we fix the electron correlation problem? If we're trying to build a wave function out of just one set of orbitals, we haven't got any flexibility. What we need to be able to do is allow the wave function to be built out of multiple configurations of different orbitals. And this is what an approach called configuration interaction. So in a helium atom, for example, you have 2 electrons. The Hartree-Fock will just put those 2 electrons in the ground state 1s orbital. That gives you 95% of the total energy. But to get 99 or 100% of the total energy, you need to include configurations where one of those electrons is excited to a higher orbital, and maybe both electrons are excited to higher orbitals. So this approach involves adding together multiple configurations. How do we do that? How do we know what amount of those configurations to do? Well, we let the quantum mechanics do it for us, and we use what's called the variational theorem, where the Hamiltonian, which tells us the energy, we allow it to give us the lowest energy configuration of all of those configurations. So in my equation here, one of the few equations, I've written it out as the true wave function is sum of the Hartree-Fock, that's phi HF. And that amount of Hartree-Fock will be probably 95%. And then some amount of lots of other configurations, the sum of Ci phi I. And those individual numbers are determined by a very complicated calculation, which is, in principle, exponentially scaling with the number of electrons in the system. This is a problem. That is a very difficult calculation to do, but it is our safety net in chemistry. We know that in principle, we can do that calculation if we had a big enough computer, which means approximations to that calculation can be checked. And you can always get closer and closer to the exact calculation to check whether your results are right. Which means we can do computational chemistry without relying on experiment. But we can only do that if we have a systematically improvable approach where we get closer and closer to the exact answer until we are happy that that has converged. So if this is a really difficult problem, because the number of these configurations, if you imagine a very large molecule with many orbitals and many virtual orbitals, unoccupied orbitals, you could have put all possible combinations of electrons in each of those. That is a very large number of configurations. Perhaps we could throw some of them away. Maybe some of them aren't important. The answer is no. Unfortunately, in this sum, all of those configurations are important, especially as you get to bigger molecules. So this configuration interaction, full configuration interaction, is a beautiful approach which is impossible, and truncations of it, let's say we throw away some of the higher excited things, get worse as you get to larger systems. It sounds like we can't do anything. However, there have been some very clever theoretical chemists in the past who have come up with approaches where you can truncate your approximations, which means throwing stuff away, which don't get worse as your system gets worse. So I have a little table, and if you read a lot of quantum chemistry literature, you'll find quantum chemists love tables. They don't like graphs and pictures. They love producing numbers. I don't like that many numbers, but I want to show you some important numbers here. And it's the errors you get when you do calculations, taking a typical molecule and putting it apart. So if you just do quantum theory, that's this mean field theory which gives you particles. Typical errors in atomization energy of small molecules are 400 kilojoules per mole. Now that's larger than some bond energies. You cannot do quantitative chemistry with those errors. But there are approaches called perturbation theory, in this case Möller-Plesset theory. This is given the label MP2, which has a tenth of the energy, and other approaches called couple cluster theory, which we'll be using later on, which have even smaller energies, 1/100 of the error in the energy. You can start doing calculations which are predictive at that point. So the downside of this is as you go to those higher levels of theory, the calculations become much more expensive. The scaling of Hartree-Fock theory is cubic, the size of system. So if you have n electrons in your system, your calculation takes some time. If you have twice the number of electrons, your calculation takes 8 times as long. That's about an okay thing to do, but very large systems are difficult. To get accurate energies with couple cluster, and here I'm going to single out couple cluster singles, couples with perturbative triples, that is the bold line in the table. This is known as the gold standard of quantum chemistry. It gets errors within what's called chemical accuracy of about 4 kilojoules per mole, but scales as the 7th order of system size. That means if I double the system, if I go from 1 water molecule to 2 water molecules, it takes 128 times longer to do that calculation. You will find in the practical sessions, we're going to use some couple cluster theory, and you'll find it frustratingly slow on some of the larger molecules, and sometimes you just have to take time. Later on, I will talk about further approximations called low scaling and linear scaling methods, which make this a lot faster. But it's important to appreciate that they are also approximations, to the correct theories which I'm talking about here. So if you can do coupled cluster theory, you should do coupled cluster theory. It will give you essentially the right answer in almost every system. I've talked about ground states. So if you leave a molecule on its own, doing nothing, it will be in its lowest energy state. But a lot of chemistry nowadays involves an excited state of the molecule. If you shine light on a molecule, the light will be absorbed and will take an electron and put it into an excited orbital. And to calculate those states is a lot harder in quantum chemistry. There are some methods to do this. You can just say, I would like my electrons to be in different orbitals, and do what's called a delta SCF calculation. So you can do a Hartree-Fock calculation and hope that you can find an excited state. This can be difficult, however, because all of the methods we use for Hartree-Fock try to find the lowest energy state. And so finding these excited states is difficult, but possible. Another approach is called configuration interaction singles, and this is available in a lot of quantum chemistry software, and it gives you excited states that are single excitations, where you've taken a single electron and put it to an excited state orbital, to the same energy quality as Hartree-Fock, which means differences in those energies might be reasonable for looking at. So a place where this would be important is looking at UV visual absorbance spectra, where you're trying to calculate what is the energy of the photon that is absorbed by a molecule. That corresponds to the difference in energies of the ground state and the excited state. And these will be reasonably well calculated with configuration interaction singles, but may be off by some number of electron volts. A more accurate approach is coupled cluster theory again, and the excited state equivalent of coupled cluster theory is called equation of motion coupled cluster theory. Don't ask me why it's called equation of motion. It's got a long and complicated history, but you can read that as excited state coupled cluster theory. And if you can do those calculations, those will give you very accurate excitation energies of, say, 0.1 electron volts. Right. The most aspect of quantum chemistry is called density functional theory. I didn't start with this because it's an approximation, but we're in the business of approximations. It is an incredibly successful approximation and has been widely used through the past 50 years. It's won at least one set of Nobel Prizes, and if you look at orbitals that somebody gives you, they will probably have come from density functional theory. If you talk to somebody in material science or physics, they will almost certainly assume that when you're doing a calculation, you are doing density functional theory. And it is a theory which has the most citations of any theoretical methods in the world. I'd prefer not to receive software updates. Well, we'll see what happens if I click on this. Okay. So, let me tell you what this slide hides. Density functional theory in its raw form looks just like Hartree-Fock theory. It's a one electron theory where you put electrons in orbitals and you build up the density of a molecule out of those orbitals. The background theory is more complicated, but is rigorous. I haven't got time to go through it. The problem is finding the energy as a functional of the density is difficult. So in Hartree-Fock theory, we have a wave function. It's very complicated, but we know how to get the energy of a wave function. In density functional theory, we build a density, and in principle, it is shown there is a way of getting the energy from the density, but we don't know it. So what do we do? Well, as scientists, we say, let's try and find that approximation, or approximations to do that. And people have been doing that for many, many decades. So, the way that approximation turns into something you will see is something called the exchange correlation functional and the exchange correlation potential. Effectively, what it's done is it's taken those very short-scale interactions between electrons and folded them into a potential energy surface which the other electrons see. It may seem like magic, and it feels like magic that that is possible, but there are rigorous theoretical ways of showing it's possible. However, we don't know exactly how to do it. So there are approximations involved in density functional theory where we approximate the exchange correlation functional. I have a few different levels of approximation here. One bit too far. Now, density functional theory can be treated as a black box, which means you give it your positions of nuclei and it gives you an energy. But it has one turnable wheel you can give it, and that is the exchange correlation functional. And there are on the order of 20,000 possible density functionals you could build out of combinations of things people have put into density functional theory. And so you have to decide, as a computational chemist, what particular setting on that dial you want to choose. And there is a hierarchy called Jacob's ladder. This is a term coined by John Purdue, and he saw that on the Earth we have Hartree-Fock theory, which isn't very good. And in heaven we have full configuration interaction, the best theory possible that's perfect. And we are creating a set of rungs going up to heaven to get better and better density functionals. Those have names. You might not be able to read them, but I will tell you that the lower rungs are not very good. So they are usually fairly cheap. There are approaches based on just the density, which works in metals, basically. Then there are approaches based on the density and the gradients of the density. These are called generalized gradient approximations. And there are some functionals I've listed on the slides which use these, something called PBE, and this is very commonly used in the material science and physics community and can predict a lot of simple materials like crystalline silicon or diamond, for example. But it doesn't, in its approximations to the exchange and correlation, it's not as accurate as it could be. The next set of steps up involves going back to Hartree-Fock theory, pulling the exchange component of Hartree-Fock theory, which is crucial for electrons lowering their energy when they're the same spin. And those are called hybrid functions. In quantum chemistry on molecules, you should probably not use anything less than a hybrid functional. The most popular is called B3-lip. Don't worry about what that means, but it's a calculation which I think you'll be doing later, maybe. Yes, okay. And if you were to go to an arbitrary computational paper in the literature, somebody will have probably used this function. There are even more expensive approaches above that. I'm not going to have time to talk about those. But importantly, because you have a choice, you have to exercise that choice very wisely. And sometimes you might not be right in your choice. So you should test your choice. You should pick 2 or 3 or 10 different functionals to do your calculations. And those calculations, if they give you the same answer, give you some confidence that you're doing the right thing. Because all these functionals are approximations. So, if you want to have more confidence than just checking against your own calculations, there have been many studies in the literature showing what functionals are good at doing what types of problems. You can't see any of the details here, but there are some colors. Red is bad, green is good. And so people have done calculations on all sorts of types of reactions, isomerizations, bond breakings, dispersion interactions, where two weakly bound systems come together, and they will tell you what functional is good for those calculations. Read that literature, use it wisely. Remember, if you do computational chemistry, if you don't do a good calculation, you can get rubbish, garbage in, garbage out. So you must check that the calculation you're doing is appropriate. So, density functional theory, incredibly popular, but has errors on certain types of systems. Dispersion interactions are not usually included. Those are the van der Waals forces that hold together simple molecular crystals and things like hold geckos to walls. They are weak, but there are many of them. They are always attractive and they always hold things together. And if you ignore them, your molecules will eventually fall apart. So you must add those onto your calculation for anything other than the very smallest systems, and there's a range of corrections you can do that with. Density functional theory is still not very good at pulling apart bonds or doing calculations where there is more than one configuration which is important. So you can do a calculation, but you need to be extremely careful as to whether you've got the right state or whether your calculation is good at all. And I think I've talked about effectiveness as well. So, density functional theory can do excited states as well. The fundamental theorems underneath it are ground state theorems, so it's very good for ground states, but they have been extended to excited states. My best advice in this is, if you can, do something called delta SCF theory, or delta DFT, where you find a ground state and you find another state, an excited state, in density functional theory, and take the difference in energies. Those two may have errors, but they will generally cancel each other out and give you good, fairly good quality energies, maybe to half an electron volt. Another approach, which is very popular, is called time-dependent density functional theory. This involves basically zapping your density functional theory calculation with light at a certain frequency and finding out when it breaks. The computer does this for you, you don't need to do it. It tells you when the molecule would respond to an excitation of a certain frequency, and that corresponds to the excitation energy. Unfortunately, that calculation is very approximate and depends very much on the functional you are using. So you have to treat those with care. There are functionals which deal with excited states better than others. So, what things can you calculate? I've given you a huge range of methods in quantum chemistry, and basically I've told you they give you an energy. And well, energies are good, but they are not all you care about in chemistry. However, most things you do care about are related to the energy. So, if you care about where are your electrons, or your dipole moments, well, that's related to the wave function. Okay, we can get that out from our quantum chemical calculation. If you care about forces, so I talked a little about classical approximations, you can run a calculation called ab initio molecular dynamics, where you start your atoms off in a certain place, you do a couple cluster calculation, and then you calculate the force on each of your atoms, and you move it slightly. And you keep on doing this with small time steps, and it moves around with classical, effectively, dynamics, and can produce some simulations. So Ross will be talking about force field approximations of that, but you can use quantum chemistry to do that. To get those forces, you need to basically look at how the energy changes as you move your atoms. And your computer programs will do that almost automatically in most cases. The more expensive your calculation, the harder that is to do. Other properties are vibrations. So Nick talked about IR, infrared, yesterday. Now, the stretching of molecules is all to do with, at the equilibrium geometry, how quickly does the energy go uphill? That is the second derivative of the energy, and your computers can calculate that too as well. And that gives you what are called the vibrational normal modes. Related to those types of calculations are things like NMR. The energy and the wave function at the nucleus are very important for calculating NMR. And to be able to predict NMR, you can do that if you can do these second derivative properties. Now, you don't need to worry about the maths of that. Your computer programs will generate those for you. Another important property you might care about is my molecule stable? What is the enthalpy or the free energy of formation of my molecule? That is something that quantum chemistry is very good at calculating. The enthalpy is easy, that just corresponds to the total energy. The free energy is more difficult because the free energy of a molecule involves taking into account contributions from all of the vibrations and their 0-point energies, and so is a more expensive calculation which needs the second derivatives of the energy, but it's possible. And all of that can come out and is very routine in many software. It just prints out the free energy at 298 Kelvin. You can analyze it and give it any energy at any temperature you like. Right, so we're getting near to the end. So things you have to be careful of. What are called multi-reference systems, where if you draw out a molecular orbital diagram, it's not clear where you should put your electrons. If you have a transition metal, for example, there are 5 d orbitals which are essentially degenerate. Which orbitals do you put your electrons in? You can't tell in advance, which means you have to allow all possible occupancies of that. This is done by what's called a multi-reference calculation, and I've got an example here where you split your orbitals into orbitals you know are going to be filled, orbitals which are probably going to be degenerate, like the d orbitals in a transition metal, or the f orbitals in an actinide or lanthanide, and orbitals which are really not going to be important. This is where your training as chemist is vitally important, because the computer doesn't know anything about this. It's really bad at guessing what an appropriate way of doing this is, but as chemists, you have seen orbitals and you've seen how the electrons interact and what are the important valence electrons. This is where your skills come into choosing the calculations. And I've just taken a picture from David's thesis here, just because he did a lot of these multi-reference calculations on lanthanides. Yeah, so this is borrowed from David's thesis there. Okay, so the types of calculation you need to do are usually called complete active space, SCF calculations. They're like Hartree-Fock, but instead of a single configuration, you have many of them using that active space. Like Hartree-Fock, they do not include correlation. They allow your choice of where the electrons go in your active space, but they're not good at necessarily breaking bonds, and they don't include the dynamical correlation where electrons repel each other. So you need to add on correlation effects to get good energies. Those methods are called perturbation theory, something called CAS-PT2 and NEV-PT2, or coupled cluster methods, multi-reference coupled cluster. All of those are available in some software. Yeah, okay, so multi-reference systems. When you break bonds homolytically, one electron wants to go one side, one electron wants to go to the other side. Transition states of reactions. Some reactions are very simple, and the electrons just sit in one configuration as you move along a curly arrow of the reaction. Others are more complicated. Pericyclic reactions, for example, where you have no particular nucleophile or electrophile, and reactions where there is a significant energy barrier, often have a transition state which is multi-configurational. You are breaking a bond and making a bond, and you have to be very careful when you're calculating those. Lanthanides, actinides, and transition metals. Radicals and open shell systems are, by their definition, multi-configurational. If you have a radical, it can usually have sat in a number of different places on the molecule, or at least be in different spin states. And maybe surprisingly, when you take very long conjugated pi systems, so lots of double bonds, there is a tendency for those to become multi-configurational. The electrons, instead of being massively delocalized, start localizing and producing unpaired electrons at sides of these systems. So, here are some caveats for the aspiring computational chemist, and the questions you should ask yourself before and during your calculations. Before you do your calculation, you should ask, is it worth doing my calculation? How accurate can my results be, and are they sufficient for the property I want to calculate? If I just want to know what the geometry of a molecule is, I can probably do a very cheap calculation to do that. If I'd like to calculate the enthalpy of formation of a molecule, I need a much more expensive calculation. So you must choose your calculation carefully. Has somebody checked whether this calculation is appropriate in the past, or do I have to do it? So that goes back to the benchmarking tables. If people have used, say, your density functional for these things before, you can probably assume it's a good thing to do. You should check yourself, however. Am I looking at the correct electronic state? Ground states are boring, usually, and often quite simple to get. If you are looking at excited states of chemical reactions, and those are ones often involved in energy capture, photoexcitation and such, deciding whether you're looking at the correct electronic state is difficult, and this is where sometimes symmetry or looking at the orbitals is very important. Similarly, if you are taking two pieces of quantum chemistry software and having them talk to each other, check whether they are looking at the same state when you're trying to get them to calculate. I have seen so many calculations where one bit of software produces one state, another bit of software produces another, and somebody's assumed they're the same. That you have to be very careful in science. You have to check everything. Have I converged? Can I do better calculations to check my results? That's always a good question. And I've talked about the different states. So that's my introduction to computational chemistry. Sorry, it was a lightning one. Good luck with it. Enjoy calculating, and I'll be around if you have any questions. Thank you.
Thank you. Thank you. Please, another round of applause for Dr. Alex. Thank you. Thank you so much. That's a lot of machines talking. Ah, wow. Baptism of fire. No more analog chemistry, no more analog quantum chemistry. All right. So the next on our program, we're in Ambassador Program launch, which will be done by the founder of Aodi, Dr. David Izuogo. And before he comes up, a little bit about Dr. David. Dr. David Izuogo is a graduate of Pure and Industrial Chemistry, UNM. Let's claim our own clap. And he holds a master's in nanoscience from Tohoku University, Japan. He completed his PhD in computational chemistry at the University of Cambridge, where he investigated materials that hold promise for single molecule magnet behavior, for quantum information process, spinotronics, magnetic refrigerating, and medical imaging, among others. David was a research associate for the Education Sub-Saharan Africa and contributed immensely to the research and publication of the 2021-2022 African Research Output on the ESSA database. He is the founder and the chair of trustee of Africa of Our Dream Education Initiative. Please, ladies and gentlemen, could you stand to your feet and let's do honor to whom honor is due. Put your hands together for Dr. David Izuogo.
I'm not sure the standing part was. Okay, so there are a couple of things. I thought that when you listen to the competition, the theoretical things that Alex was going to say, I know it's enough to like lit your brain with fire. So I thought, okay, it makes sense to sandwich a campus ambassador program between that and then another competition session that is coming later. Just so that we don't need to get water to cool people's brain, you know. So, like yesterday, I did mention that today we'll be launching the Campus Ambassador. It's a flagship program by the Africa for a Dream initiative. Hopefully this slide will be up and we can dig deeper into just showing you some of the things briefly on the first page that Aodi is kind of involved with. I think sometimes it makes sense for you to take the time to say, these are the key things that we actually do, so that when people hear your name and think about themselves, they know what it is that you can offer them. And like I did mention, Aodi was founded in 2017. That was like 1 month after I arrived Cambridge for my PhD. And the reason that was done was I looked at my personal background. I came from a poor family. At some point, I never knew I would be able to see the 4 walls of the university. In my SS3, when my peers are discussing about the universities they want to go to, the courses they want to study, I'm always quiet. And when you ask me, I'll be like, because I know I'm not going to go to a university, right? But along the way, my aunt came on board. I was like, okay, I have this restaurant business I'm running. If you can help me put it together, I might be able to fund your university education, right? And that was how all of that started. So there's always someone somewhere who is trying to provide that steer to keep me moving forward. However, after my second year, after my first year in UNN, UNN is very far from Imo State, so I'm not able to usually frequent home to support the business. So the business started kind of failing, and she couldn't fund the education anymore. So at that point, I had 2 choices: drop out of school or do something to fund myself. Nobody knew what was happening because even as of my first year, I ran for the financial secretary of Faculty of Physical Sciences. So people would, I was a FinSec, people wouldn't really know what you're going through, like within, right? Then I had 20,000 Naira at that point. And I had a whole lot of things to do in that second year, first semester. The first thing is pay my tuition, the second for my accommodation, and then still have money for my feeding and upkeep, okay? So I was like, which one do I do? And even if I do that, where do I get the rest of the money to do the rest? That was when the idea of Chooks Academy came on board. I thought that in my first year when I came in, most of you might have heard it, people would tell you, Chem 101 is a no-go area. Like a lot of people find it difficult to skate through this. So I was kind of a bit scared. I did all manner of marathon tutorial classes just to get myself through that course. And I scored around 90 something, in the first semester. And I had a whole lot of materials that I've used to prepare. So I thought maybe it makes sense to use this material to produce a solution manual that could support other students to succeed the same way I've succeeded. And then I produced the first solution manual, Chooks Academy. I started running free tutorial classes. And that was how the whole Chooks Academy of a thing came through. So the money I realized from selling that solution set was actually what I decided to use that to support my education going forward. Until my second year, I got the scholarship exchange program to Hokkaido University, and then later on to master's at Tohoku University in Japan as well. And then from Japan, even though I had my PhD fully funded to continue my program in Japan, at that point I was driven by the desire to commercialize my research. I looked around all the institutions you have around. When I look at my lecturers, my researchers, most of them do research because they want to, make publications, gain promotions, and all of that. I thought I could change that narrative. I thought, is it possible for me to do research that could produce something that will solve societal challenges? And one way to do that is through collaboration, to collaborate with a lot of people. And I thought that computational techniques could allow me to collaborate across different fields, bring researchers together to actually do research that will output something you can use to solve societal challenges. That was the idea. Then I decided to move into computational. Wrote Alex in Cambridge, told him about my research in Japan, and told him, okay, I saw on your website that you're interested in single molecular magnets, understanding what happens in the computational world. This is what I was doing, and these are the challenges that I think computational techniques could use to solve that. And that was it. He wrote back, we jumped on a call, Skype, then Zoom was as popular as it is. We spoke, and then he was like, yeah, I'm happy to supervise you, submit your application. And that was it. I submitted, I went through the entire process. I was offered a conditional offer. Later on, I got like 3 different scholarships, but I had to then take one because they wouldn't let you take all 3, right? But then I strategically wanted to identify with all those scholarships. I said, okay, 3 of you should come together and decide how you want to split, who pays the tuition, who gives me the stipend, and all of that. I just want to be identified with all of you. And that was what happened. But what that meant is that I now have access to the network of those 3 different scholarships, okay? Which is why yesterday I told the highlights of me being in Cambridge was the network I had built across board. So after this, 2 weeks after I arrived Cambridge, I contested to be the president of international students. And somehow I won that. I don't know how it happened. But at that point, that brought me closer to the school authority at the college, at the university level, and all of that. I started interacting with people, and I saw this passion within anyone you speak to at Cambridge to support something that helps minority groups. There was this campaign to bring a lot of Black people in Cambridge, give access to the minority people that would ordinarily not be able to come to Cambridge. So I keyed into that through the Cambridge Trust president, Helen Bennett. We built this bond, and she was so passionate about, being able to offer scholarship to brilliant African students coming to Cambridge and all of that. And then I asked myself, doing this on my own could have some limitation. So maybe it makes sense to set up an organization that could collectively be a platform that offers all of these supports to African students. And at that point, the birth of Aodi was kind of given. From then onwards, we've been doing a couple of things. I don't know if this slide is still coming. We've been involved in a series of things, but we started with the mentorship. That was the first thing we started with, because it was easy for me to just find a couple of folks back in Cambridge, academics, PhD students, people who've gone through the same process to come to Cambridge to say, hey, this is what we're trying to do. There are a whole lot of amazing African students, brilliant students, who are down there, who do not have the opportunity to have the kind of education you have here. Will you be able to support these people to make competitive application? Because we realize that a whole lot of people have got so many things they've done to stand up, but they're not able to sell themselves in the application. Either they're not able to articulate their personal statements, or their CV is not well written, or the application essays they've written is not well written, all of that. We thought that the people who have gone through the tedious, rigorous application process of Cambridge should have the experience to support other people. And so we decided to start with that mentorship. Then we realized that when you do mentorship and someone is able to get admitted to a university like Cambridge, you are made a conditional offer. And one of the conditions you need to fulfill is the financial aspect of your funding. I think my tuition was around £37,000 a year. So that's, I don't know, depending on whether you decide to use a parallel market exchange. As a normal Nigeria, if I need to pay for my tuition, probably use the parallel market, because there's no forex exchange for me to do that. Even if there is, it's limited. There's some kind of cap. But if you convert that, it's almost over 30 million naira in a year, just for tuition. So you can imagine only very few people, maybe politicians, could afford that kind of thing, you know. So I decided that when we provide mentorship, we should target scholarships. So you're not just telling someone, this is how you do X, Y, Z, just to get admitted. You are telling someone that because you want the person to get admitted, and as well as be able to access the various funding that we have. I think Cambridge is the #1 university when it comes to the number of funding you can have. Cambridge trusts have access to more than 100 partners that provide them with some money.
Okay, it's finally coming. So the mentorship is there, and you have the scholarship, which we don't give you the scholarship, but we support you to apply and access all the scholarship that you can get out there. And then we have a research partnership, like a program we call Partner Africa Project. We started in
2018 with Covenant University. And basically what we do is we take some folks from Oxford University, Imperial College, Cambridge, bring them down to Nigeria to spend like 3 weeks, 1 month. We did that with Covenant University, interacting with the staff members, delivering lectures, and building that kind of research partnership with them. Okay. I think the problem we have with that is that it's kind of capital intensive. You need to fly people. The university you are coming to need to be able to cater for maybe the accommodation, the feeding, and all of that. We don't have the financial power to do that yet. So we kind of partner with universities that could do that for the people we are bringing. But then the staff members and students can benefit from the program. Can we go to the next slide? Okay, don't worry. Okay, so that's the list of the things we can do: mentorship, scholarship, career opportunities, research partnership that I've mentioned, equipment donation. So another thing
we try to do is to look around universities who have across and see if there are researchers that want to give us some of the people that sometimes we're able to actually access some funds. Like last year, we got some money from Cambridge Africa program to procure brand new FTR machine for the department. So these are some of the things that we try to do: access those funds and those equipments where we are, and then be able to bring them where they are needed. Okay, it's one of the things that we try to do. And then workshop like this, training, seminars, lectures, try to facilitate them. We don't have the facilitators in the house, but we have the networks that can help us bring in people to be part of the nature, just the way we've done it. So this summer was just a summary of Aodi, how it came about and that. And then I just wanted to say that this is not something I'm the one speaking here about. I'm not just the engine behind this entire got amazing team. Couple of guys who came in as co-founding trustees. Chidozie Ojobo, who used to be microbiology. We have Chinedu Moye, who used to be computer science here. also look at it, she's here, she's been amazing. Like, in fact, I don't know what I would have done without her in terms of setting up things. She's agri-economics lecturer. So these are a couple of people that came together. Joseph, who happens to be my classmate, and then came together and decided to say, okay, let's move our resources. He's passionate about making impact in the lives of people, and we're able to send this collaboration. Since then, they have always been contributing, and then the rest of the team, hopefully at some point we're going to get some of the AODI team members and some of the education come forward so you guys can join in telling me thanks for the amazing work they're doing. And all of these guys are doing this for free. I'm not paying them, it's voluntarily. They're taking it with passion because they know what they're trying to impact and the benefit of it. So I'm really, really proud of that team. I don't know what I'm not doing now. Okay, then we realize that it makes sense for you to have tailored support. And I understand that chemistry department doesn't have an LMR because I'm not here and I have links and all of that. But if you ask me now, what is it that chemistry department is really like? Yourself, what do they have? What support do they need? I don't know. Because I'm not there. I don't have connection with someone who is there. Okay? So we decided that we should expand the things that we do across different universities. And that was where the campus ambassador came up with me. We thought that we could have access to students who will represent us on campus, who will be our eyes and ears on campus, who will be able to tell us this is what is going on. It's not just going to be chemistry, it's going to be every department should please have a member of that investment program. Each department member will have a lead, and then you will have someone who oversees the entire campus investment in the university. Okay. So these folks are going to help us and to strengthen our presence and actually have tailored support to what the university system needs. Just like I said, bring AODI closer to the students to enable tailored support.
To the students to have presence across leadership, professional and career development, increase impact of what we do to students, lecturers across board. So who will be involved? We have the AODI team. We are going to be there coordinating and doing all manner of things. Then we want the university staff to also get involved in this. The university staff, you might not be a campus ambassador, so to say, but if the students are saying, we think that we need something like a mass spec, is going to aid our research and stuff like that. If AODI is able to find resources to do that, we are not going to give those resources to students. So we need that partnership. We need to have that cordial relationship with the staff members of the universities and the departments we are going to support. Then research institutions, tertiary institutions, partner organizations. These are partner organizations who would want to, support academic learning, but at the same time, maybe, try to also showcase whatever it is that they have to students. On the other side, we just have the initial set of universities who want to pilot this, and we're starting here. So the success of this program right here is going to then determine what happens next, if it's actually the effective way of trying to connect with campuses and all of that. So if you happen to be our ambassador, I think it makes sense for you to know why we are choosing you and what you are going to be doing for us. A worthy representative of AODI team at various institutions, serving as intermediary between the organization and the students, who help to foster the fulfillment of the organizational goals and projects. So that is your summary of what I've just explained. And what are we looking for? We want to say, okay, we think you can be our campus ambassador. some of the characteristic qualities we are looking for is it should be, because you will have some distraction to support programs. I don't know, but it looks like it doesn't make sense for you to bring a student who is already struggling with his study to start having distraction that comes from AODI. Even though there's a whole lot of things you can benefit from, I think we want to focus on, students who are of good academic standing to be able to come on board to help us define what we're doing. And then the second thing is that you are going to be doing a whole lot of selfless things. Someone called me and was asking me how much we are charging for this thing we are organizing. I say it's for free. He said, what about your mentorship program? I heard you run mentorship. I said, everything we do that's why we're a charity. He couldn't believe it. He still think that somewhere, somehow, there is something David is getting from all of this. It just cannot be free. I just want to tell you, standing here before you, this event, for instance, was partly sponsored by Royal Society of Chemistry in UK. They are the only one that gave us some money, about 50 to 60% of the total amount we are spending. The rest of what is used for this is not coming from anyone. Okay, so I'm not getting anything. I'm giving out, all right? So, because I don't believe that there is something material you need to get before you can impact lives. Because when I think back and say, Cambridge University spent hundreds of thousands of pounds just for my PhD, and they've not asked me to come back and give anything back to them or pay in any way. So why wouldn't I have the confidence and that selfless mind to support other people in the ways that I can? So when I do this, I have no strings attached. I don't expect anything from anyone. What I just want is, I just hope that the events, the things we do makes impact. That is what is most important to me. So we need people who are committed to improving the lives of others. Someone that you are passionate, you know that what you are doing is going to support your fellow students to gain something somewhere. And because of that alone, you are motivated to do good. Those are the kind of people we are looking for to be our campus ambassadors. Effective time management. Of course, we don't want you to support AODI to drive our initiative, and you're not able to manage and balance your academic program with what you're doing. So you should have a good effective time management skills. Leadership quality. You need to lead others. You need to be able to inspire, because sometimes you might be saying something that someone beside you might benefit from. They are listening to you, but they don't even know how they are going to benefit from it. So sometimes you need to push extra hard, okay? Sometimes you bring something and you're trying to give to someone, the person doesn't even want to collect it. He's trying to prevent you from even giving him that. But you're giving him something that he's going to benefit from. So you need to understand that you don't just say, oh, you can do whatever you want. I'm trying to help you and you are resisting. I'm just taking what I have. No, that's not the spirit of AODI. What we try to do is that even when you push, we try to push ahead to convince you that we are doing good. We are trying to do this for you. So we need campus ambassadors who understand that and are able to help us with that. And of course, we need a whole lot of people to benefit from the things we are doing. If I can spend 100,000 to educate 20 people, but at the same time, it's physical events, but at the same time, I can do something online that could also add benefit to additional 500 people who are streaming online. I will go to any length to increase that 20 number to 500, okay? And so you should be able to promote the things we do online so that other people will know about what we're doing. And then passionate for professional development. Sometimes you need to feed yourself, right, before you can get the strength to feed other people. So while you are trying to support us, to support other people, we want to also make sure that we help you with your personal, professional career development. So you're going to benefit from every other thing that we do at AODI. And then your role. If you become a campus ambassador, what will be your role? You represent Aodi at your institution, that is provide career opportunities connected to that. You craft and run tailored events supported and financed by AODI. So all you need to do is to think, what events would make impact on my fellow students? What will it cost? You have a conversation with AODI. We source for the fund. We do that. But we need to definitely see the impact that that is going to have. Because thinking about the programs you are running on your institution. Advanced AODI management of student needs. Advanced AODI on management of student needs. Okay, so these are the things you are going to be doing. I know some people are now saying, yeah, I know, I want to do charity, but what is the need for me? Okay, so we understand that naturally humans are selfish, including me. There's no doubt. You think about yourself before others. So we recognize that. I just wanted to highlight some of the things that you are also going to benefit. Okay, so when you are doing good to others, but at the same time, you are also doing good to yourselves. Leadership skill development. On our own part, we'll ensure that anyone who is a campus ambassador has those skills that are required for you to be a leader. Even if it means going out there, sourcing for leadership experts, giving you training, whatever it takes. Okay, that's for you. Professional development as well. We want to make sure that if you're a campus ambassador, because you're an ambassador, you're representing us. So your success is also our success. So we can proudly tomorrow say, yeah, he was an ambassador, he benefited from the programs we've run. Today he's XYZ and all of that. So we want to support your professional development. And as well, give you access to the network of scholarships, employment opportunities that we have. And of course, there are going to be some branded AODI merchandise that we give to you, like T-shirts and the rest of them. Access to all the network we have, international and national, and the rest. Access to the AODI team. All our trustees, most of them some are in Canada, some are in the UK, US, some are here in Nigeria, and all of that. Have access to all of them. Tailored career support. I think one of the benefits is that you are closer to us and we know your strengths and your weaknesses, and we're able to support your career development and all that. Internship opportunities. One of the things that AODI is doing now is to try to partner with some firm to see how we can bring opportunities to students. Maybe a couple of months from now, we're going to start that with McKinsey and Company and see what we can do. And apart from that, AODI also have paid internship that we run every 3 months. We could continue with the same set of interns and just tell them, okay, continue running internship, but no, that's not what we want. We want every 3 months to recycle our intern and bring in new people to benefit from the career development and growth that the organization offers. So we look forward to using, picking some of these interns from our campus ambassadors. It's paid internship. It's not, you don't do that particular one for free. And then, of course, the last two, which is research partnership and access to research grants. This would be for lecturers who are kind of involved in what we're doing. We'll be able to, provide those tailored support, and these are grants that are available. This is what it means for you. This is how you can access them, and all of that. All right. So if you're interested, you'll be able to visit AODI website to make your application. After that, you can see the process. So we don't just pick that you've submitted your application does not necessarily mean that you'll be selected for the program. So, but now that you've listened to what it is, you need to be sincere to yourself and say, is this what I want to do? Will I be able to do this? If yes, go to that application and tell us why you want to be a campus ambassador. Spend time, take your time, don't rush it. Submit your application, we'll review it. And those will think that, okay, maybe what they're saying is making sense. We want to confirm that by inviting you for an interview. So we have just an informal conversation to probe your passion and all of that. And if we think that you're a good fit, you come on board the Aodi family as a campus ambassador, right? So that is it. Thank you. I don't know. Do we have the list? So I wanted to use no problem. I thought that just to launch this, we have a couple of people who did make application. And I've just looked at this. I will still talk to them, hopefully. But if you are here, it would be nice to, come forward. I don't know if you've been given the branded T-shirt. If you can wear that, that is fine. But if you've not been given that, let's get their own T-shirts forward. So we can use these people to launch it. Ikenna Emmanuel Umike, Essien Torio, sorry if I murdered that name, Oji Chinwotito, Odezulu Juliet, Waneke Praise, Peter Ene, Pascaline Mama. Okay, maybe I can come down, also have a snapshot with AODI first ever campus ambassadors. Okay, thank you so much. I've not had time to interact with you, but definitely we'll talk after this. But I really appreciate you putting yourself forward to drive the dreams and aspirations of what the Africa of Our Dream Initiative wants to do. Okay? So thank you so much. All right.
Please put your hands together for Dr. David Izwogo. That's an amazing presentation. Thank you, sir. All right, so we're going on a short break. And I think like yesterday, we are going to sit and wait for them to bring what we're using for the break. After that, we'll continue. So please relax. Please do not get up from your seat, except you are part of a serving committee, so that we can get to you. Our break will be for 15 minutes, and then we'll continue. Thank you.
To jama'a assalamu alaikum ga labarin.
function, things like that. So they seem very abstract for now, but I think once you've run the calculation and you've seen a few numbers, a few orbitals, for example, a few electron densities, then I think these objects will become a little bit more concrete to you, a little bit more tangible. You can sort of see that these are things that you can calculate, and you can actually make chemical interpretation from the results. I can't really share my screen for now, but hopefully that will be sorted, in the next couple of minutes. But for now, so if you've got access to the handout, if you can open that and maybe have a look at that first, and then we'll walk through the tasks, because there are many tasks on there, and we don't need the screen to actually do the tasks because you've got all the instructions on the handout. So if you can open that, and then we can take it from there. Yep, so have you got the handout open? Yes. Okay, so maybe, if you're sitting together in one table, you can share the handout, and maybe another person can run the calculation if you've got some ORCA set up. Don't know what to do really. You want to go out there and see whether okay. So maybe if you could stand here. Yeah. Maybe I'll move closer. Just, yeah. So I was able to connect to yours, but I'm still not able to connect to the internet. So I thought I'm just going to move here to. Yeah, it's connected, right? Okay, there we go. So maybe I'm gonna stay around here. Then. Yeah. So we are going to bring the pockets down. Yeah. Okay, so if you've already opened the handout, so have you managed to get ORCA set up and such, or has that been quite a challenge? Okay, I might walk around as well. I think that might be a bit easier because it's meant to be an interactive session. So I might try to do something like that. Yeah, I think everyone's sort of struggling with the internet to actually even get the workshop. So I'll try to get something happen on the screen, and then we will take it from there. Not just the workshop, but the PDF file with the instructions. The one that was sent out yesterday. Yeah. So there was an email that was sent out yesterday, the PDF file. Yeah. So if you can open that file, that has instructions in it. So yeah, there should be an email that was sent out by the Aodi team yesterday with, quite a few PDF files. One of them is the handout for the workshop that we're doing right now, and that handout contains detailed instructions on how to get certain calculations to run. Yeah. How do we go about it? Okay, so you've got this stage. So what you do is, you don't open these in here. This is for you to create your molecule. So let's say for carbon, you might want to close these first. I will try to demonstrate this. I can actually get my screen shared, but you can close. Again, you can close those. Anyway, it doesn't matter. So on here, what you can do is you can create a carbon atom, put that there, and then you can make another carbon, for example, or you can make another oxygen. So this is how you create. I'll try to demonstrate this one there in a bit. Yeah, sorry. I think they might be able to get me. Oh, excellent. Right. Thank you very much. Okay, so right, so now we are sort of trying to set things up. So I think we'll try to be quite quick at this stage because it's. Yeah. If you can also access YouTube, you will be able to see the screen a lot better on there as well because this is currently being streamed on YouTube. So if you have trouble looking at the screen, go to YouTube instead. You'll be able to actually see some of the commands a lot more clearly on there. So this is sort of an overview. Yeah. So this is sort of the overview for the workshop. We are going to try to do some setting up. Hopefully you've got Orca, but if you haven't, that's fine. If you can't really do anything, try my best to actually go through some of the calculations. You can actually see how it's done. And then when you go away, after today's workshop, when you're at home, when you've got a bit more time, maybe on the weekend, when we can go to somewhere that has some internet access, you can download Orca, and then you can go through this, the calculations again. So hopefully just to give you a flavor of what you can do on your computer, provided that you can get the software, and hopefully once you've got through the initial steps, it should be fairly straightforward. Okay, so if I sort of switch out like this, you can see my screen as well. Excellent. Can you though? Yep. So that's my terminal. Can you see something like this? Actually, I don't know if it's being shared. So hold on, give me a second. Can you add me again? Thank you. Yeah, so I just shared again. Okay. Okay, so hopefully you're sort of looking at the right. Okay, maybe not this yet. I'm going to try to switch in and out between some sort of terminals where I can run some calculations and then actually show you output files and such. But if I can't do this, that's fine. I've got a set of backup output results that I can still show you so that you can see what sort of output files you can get and what sort of information you can extract from these files. Yeah. Don't worry too much about this, it's just the way I work, but you can run your calculations in other ways as well. And Alex and Nick are walking around to sort of assist people with running calculations. Okay, so let's see if that actually loads. So the very first thing that we'll need to do today is to set up our case study. So in today's workshop, essentially, you're going to use a very small molecule, formaldehyde. So this is just CH2O, so that's, carbon with a double bond to oxygen, and then 2 hydrogens attached to carbon. So I hope you're all familiar with formaldehyde. So the one thing that we need to do is to set up the formaldehyde molecule. And this is the same for every time you need to run a calculation. Before you need to run a calculation, you have to create your molecule first, so that the calculation knows what molecule it is running on. Let's say you're investigating the electronic structure of, say, a transition metal complex or some sort of protein, you need to have the structure of the compound that you're studying first. There are many ways to get such structures. This is a very small molecule, so we're just going to create a structure ourselves. But in reality, let's say you've got a very big protein, you need to go to some sort of protein database to get the actual structure of the protein. So Nick talked about the Cambridge Crystal database structure yesterday. So that is a very huge database that has basically a lot of protein structures that you can get from. So that's for proteins. But for small molecules, you might either want to draw them yourself, or you might want to sort of get these molecules from a paper, for example. They might have coordinates of these molecules. If you've got molecules that have been studied under X-ray crystallography, you can get the X-ray data that has the coordinates of these atoms as well. So there are many ways that you can create molecule structure for your study. But the way that we're going to use today is to go through IQMore. IQMore is a very simple but very useful molecular visualization software. So in this instruction, it should tell you to install IQMore. It's quite easy to install. Once you've got IQMore, you can open it. So I'm just opening IQMore on my computer. You should see something that looks like this. So how do we create a molecule? We want to create a structure for formaldehyde. So formaldehyde has a carbon, so essentially you choose carbon, and then you just click on there, that's going to be your carbon atom. And then you want an oxygen connected to carbon, so you can choose oxygen. And then just basically draw it out from the carbon. And it's a double bond, it's C double bond O, so you might want to give it a double bond. It looks nice, but when you create a molecule geometry, double bonds don't really matter, because double bonds are a concept that we sort of create, that we invent to talk about chemical bonding. Atoms don't really care whether they are bonded by a double bond or a single bond or triple bond. Those are, concepts that we use to describe bond strength and bond length. But I mean, the point is, it doesn't really matter whether you put a single bond or a double bond. And then, of course, you need to add hydrogen to this, because you're still missing 2 hydrogens around carbon. So you need 1 hydrogen there and 1 hydrogen there. So that structure looks sort of like formaldehyde. It's a bit distorted, but it's fine. It's close enough to the formaldehyde structure that we would expect. What we want to do is just basically do an energy minimization. This is a very simple energy minimization process that uses a very simple force field model to minimize the energy of the molecule. This gives you a sensible enough structure to start. But what else you can do is to symmetrize it, for example. You can go to build and choose symmetrized molecule. This will allow the molecule to be symmetrized, so that it has, sort of nice symmetric shapes, essentially. You can also translate it to center, so that it's at the center of the, at the origin of the coordinate system. And once you are done with this, you can save this structure as an XYZ file. An XYZ file is a type of file that contains, a molecular structure information. So if you save it as an XYZ file, you should be able to do this. I'm just going to save it maybe somewhere here. This is task, is it 2.2? Maybe it's 2.2. So I'm just going to save it as, or maybe it's 2.4 actually. Hold on, I'm just going to quickly check. It's 2.4, so I'm going to put it in there. So I'm just going to give it a name, which is CH2O dot xyz, right? So that's your structure that you're going to use for the rest of the workshop. So I'm just going to quickly open the file that we have just created. So that file is in here. I've just created that file, and you can sort of open it with any text editor that you have. So I recommend the use of Notepad++, because it's quite nice and it's quite modern. Notepad is fine as well, but you should be able to see this file here that contains the XYZ coordinates of the 4 atoms that make up formaldehyde. And this is in this format that can be understood by, Orca when it needs to read in the geometry. So once you've created this file, that's basically the role of task 2.4 here. It's just to create the structure of C you can use for the rest of the calculation. Let's hope it will switch back to this soon. Okay, so this is just to set up the case study. This is just geometry of formaldehyde that we are going to use for the rest of the session. Okay, are you happy with this? Does that make sense what I'm doing? You might not be able to do this yourself, but what I'm trying to do here is to create the structure that we are going to use for the rest of the calculation. You need some sort of structure to calculate on, right? So here we are just doing that. And then of course later on we're going to use the same structure, but we're going to calculate we are going to apply various different methods on this structure to do different things. And hopefully throughout the workshop you will see what sort of information you can get out of the calculations. All right, so don't worry too much if you can't actually do this live right now, because like I said, the handout should have all of the information. It's a lot more detailed than this, so you can go back and try to follow that in your own time. Okay, so the first thing that we will do is to do some ground state calculations. So you've heard from Alex this morning that there are quite a few different number of methods to do ground state calculations for molecules. So the simplest method that you can do is Hartree-Fock. So in this task, let's do a very simple Hartree-Fock calculation for formaldehyde. All right. So the way that we run the Hartree-Fock calculation using Orca means, the instructions that tell Orca to run this calculation. And that's the same for other quantum chemistry packages as well. Every time you need to run the calculation, you need to tell the software what calculation you are trying to run. And the way to do that is to use an input file that contains the instructions in an appropriate format. So the way that Orca wants, the input file to be written is in this format. It's quite straightforward. It's got these funny characters like exclamation marks and asterisk and such, but that's just the way that Orca defines its input file format. You just have to follow that. And how do I know the format to use? The way to do is to look at the instruction manual that comes with Orca. Every time you use a quantum chemistry software, you need to also look at the instruction manual that comes with it, because in the manual there will be detailed descriptions of how the input files are structured, what kind of calculations you can do in the software, what sort of results you should be expected from these calculations. So the input file format for a restricted Hartree-Fock calculation looks like this. You basically tell Orca that this is the calculation you want to do, so RHF. HF is Hartree-Fock, you know that. R stands for restricted. What does that mean? So when you do, so you've heard from Alex this morning that electrons can have spin up or spin down. It can have, one spin or the opposite spin, right? So you've got two different types of spin up or spin down. A restricted calculation essentially constrains the electron spins to be electrons of spin up to be in the same orbitals as electrons of spin down. So essentially every orbital is occupied by a spin up electron and a spin down electron, right? And that is true for all of the pairs of electrons that you have in the system. And essentially that means that, let's say you've got a system that has, say, 20 electrons, you only need 10 orbitals to describe these 20 electrons because the 20 electrons are split into pairs, and every pair is described by one orbital. And of course, for this to be possible, the number of electrons has to be an even number. You cannot have a restricted calculation when you have an odd number of electrons. We'll see an example of that later. But this neutral formaldehyde system has an even number of electrons. How many electrons are there in this system? Anyone knows? How many electrons are there in formaldehyde?
The number of electrons in formaldehyde, the oxygen there is 8, carbon is 6, and hydrogen is 2.
Because I can't do it.
8 is 2, that's 16 electrons.
I think you mean 14. I think it is 14, isn't it? 8, 10, 16. Sorry, you're all right, 16. Yeah, sorry, I was thinking of 7. That was the reason why I was thinking of 7. But that 7 was counted from 0, so that's 16. Yeah, that's right. So there's 16 electrons in this molecule. So that means that whatever you do in a restricted Hartree Fock calculation, you should expect to see 8 molecular orbitals that come out of that, and they are doubly occupied. Yeah. Okay, so I'm just going to pause a little bit to let people catch up. Yeah, so if you've got any questions, Alex and Nick are going to walk around. Okay, so you're still trying to draw the molecule, all right. So maybe I'll give you about 5 minutes to sort of draw the molecule. Right, okay, so let me start again with the drawing of the molecule. I'm just going to delete all of this and start again. So, to draw a molecule, essentially you draw atoms, right? So you click on this button here that has an element label. If you want a carbon, choose carbon, right? And then you double click on the screen or just single click on the screen to put the carbon atom there. Okay, so let me do that again. Just click once to put the atom there. And then if you want to attach an oxygen to this, then you need to go to oxygen. So you pick oxygen from the list. What you do next is to click on the carbon atom to show that the oxygen should be attached to carbon and drag out. So when you drag out, it should create an oxygen atom that is bonded to carbon. Does that make sense? So let me do that again. So what I'll do here is to click on the atom once. Sorry, so double click on the atom and sort of just drag out. It's a bit, sort of you play around with that, you'll see that it works. It's quite intuitive. Yeah. I'll do the same for the hydrogen, for example. So let's do a hydrogen here. So what I did was just sort of double click on the center carbon atom and drag out, because when you do that, you create a hydrogen that is bonded to a carbon. Okay, and I said that the oxygen has to be doubly bonded just because of valency around carbon. So I can just basically click on carbon and drag the same thing again. If you sort of do that twice, you get a double bond. Yeah? Are you able to follow this? Cool. Okay, so maybe I'll give you a few more minutes to do this, and then we're going to go back to restricted Hartree Fock. Yeah, I think it's quite important to actually get the structure first, because we're going to use a structure for all of the calculations. So, yeah. So once you've drawn an approximate structure for the molecule, you can click the button that's got like an arrow with an E on it that says minimize energy. This will simply clean up the molecule by minimizing its energy by a very simple force field model. This sort of makes the structure a little bit more realistic, because when you draw, it's quite hard to make it symmetrical. But if you click minimize energy, it will make the structure a little bit nicer. Do you have another book? Because I want to have. Do you have something that is like a book or something? Yeah. Something that is quite high, so I can put the mic like this. Yeah, it's easier with two hands. I think this actually works. Okay. So once you've got the structure that you're happy with, just save it as an XYZ file. So just file save, and then save it, give it any name you want, and that should be the structure that you'll be using throughout the session. Just out of interest, if you don't like formaldehyde and you want to do this for another molecule, go ahead. I mean, formaldehyde is just something that we use to make the workshop sort of consistent. But if you really want to investigate a different structure, you're more than welcome to do that. Maybe when you go home, for example, you can make, say, water or benzene or hexane, cyclohexane, for example, any structure that you can think of. As long as you can draw it, you should be able to then create a structure for it that can be used by quantum chemical software to run calculations. All right. I think if you can't draw the structure, that's fine. In your handout, you are given the coordinates of a formaldehyde anyway, so you can use that to do some calculations. If you can't draw the structure yourself, you can use the structure given to you to do calculations on that. I'm not going to get through this, but okay. So what I'm going to do now is I'm going to do a demo on how to run this RHF calculation. I'm going to actually show you the input file and the way that I run the calculation, so you can see how the calculation is run and how the output file is generated. It's not big enough for everyone to see. Okay. Right, so this is the input file that I've talked about earlier. This is exactly the same input file that you saw earlier, right? So in this input file here, you've got, excellent, you've got the keyword that tells Orca to run a restricted Hartree-Fock calculation. This is your basic set. You heard from Alex this morning, the 631G star basic set. So this basic set this is how you tell Orca to use this basic set to describe the molecular orbitals in your molecule. And the line below, this line tells Orca to use the structure of ch20.xyz, the file that you've created earlier, to run calculations. Right? Thank you very much. Okay. Yeah, I think that's fine. Thank you very much. Yep, I think that's fine as well. can go away. Thank you very much. Thank you. Okay, so just a recap of how I got here. So we've created a structure. Now we want to do a simple ground state calculation for the structure, right? So the simplest ground state calculation that we are going to do is Hartree-Fock. You've heard from us this morning that Hartree-Fock is the simplest wave function approach to computing the ground state of the system. So to do a Hartree-Fock calculation, essentially you just create an Orca input file that tells Orca to run a Hartree-Fock calculation, and you need to specify a basic set as well. So the basic set that we are specifying here is 631G star. You've heard from Alex that 61G star is a fairly small basic set that you can use. There are other larger basic sets, and that will give you more accurate calculations, but this should be fine for now. Right, and you also need to specify the structure that you want to run your calculation on. So I've created a structure, which is this one here, right? So what I'm going to do is I need to put the structure in the same folder as the folder for the input file. Otherwise, the input file wouldn't know where to find the structure. So I need to essentially create a new file. You can create a file using a text editor. That's fine. I'm just going to do that from the terminal because that's how I'm used to doing things. But if you've got, say, a software that can, like Notepad, for example, you can use that to create a structure, the structure file, essentially. Yeah. Essentially, what you want to do is you want to put the XYZ file that you created earlier in the same directory as the directory of the input file that you've created earlier. Sorry? Yeah, you can if you want to. VS Code is a perfectly good text editor as well. So if you've got anything that can edit text files, that's fine. Just maybe don't use Microsoft Word because it's not a very good text editor. It is a text formatting software. So if you use that to edit sort of text code like this, it won't be very good. Notepad should be a better alternative, or Notepad++ is a good one I recommend to use on Windows. If you're on Linux, you can use Vim, Emac, or Gedit, depending on what system you have. All right? So now that I've got these two files that I need to, so I've got two files here in my directory, ch20.inp, which is my input file. You can see the content of that file again if you want. It looks like it's just the input file that we need to get Orca to run the Hartree-Fock calculation. And then we've got the coordinate file that tells Orca the geometry of the molecule we are running. So it looks like this. And what I'm going to do now is I'm going to worry too much about these extensions. So when I run this command, Orca will perform the calculation. I believe it is running. So that means that the calculation is done, and you can, if you look into the directory again, you will see more files being created. So before, we only had two files, ch20.inp and ch20.xyz. So those were sort of the input files that you give Orca to run the calculation. You've specified your calculation by giving it a structure and the type of calculation you want to run. Orca then goes away, runs a calculation, and then gives you a bunch of output files that you are going to examine. So the calculation results are contained in these files that are sort of split out here by Orca.
So yeah, it's paused, so they can't even see what you're doing.
It's Oh gosh. Yeah.
I was checking and I'm like, you are still on the same.
Yeah, if anything like that, you just shout.
Yeah, you sure. Internet situation is something.
Yeah, I've just shut my screen. Thank you. Ah, excellent. Okay. 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 Yeah. But I think we're just gonna wait for these guys. So does everyone have any question up until this point? I will recap the last part because we couldn't see it on the screen, but I'll try to go over that again when that comes up. Okay, we are back on there now. So I'm just going to backtrack a little bit. So far, I've mentioned that we've created the input file for running a restricted Hartree-Fock calculation, and we've got the geometry of the molecule we put in the same directory. So what we need to do now is to run the command that executes a calculation. So this command is fairly straightforward. You just say orca. If you've set up correctly, this should work. And then you give it the input file name, and then the greater sign, and then the output file name. And if you run this, it should, it seems like it's not doing anything, but it's actually running calculations. And when this is returned, it means that the calculation is done. And then if you check the directory, you should see additional files that have been created. Some of these files contain the results of the calculation we've run just now. Yeah. So I'm going to open one of these files so that you can see what it looks like. So let's open the output file. It should look something like this. So it's got, the title orca on top. And if you scroll down a little bit, let me see if I can make this a bit smaller. Yeah. And if you scroll down, you'll start to see a lot of information that you can actually extract from the output file. the first part of the output file basically just tells you the authors of the code and so on and so forth. So the main results will come after. We've created a geometry for formaldehyde, and we run the calculation just at this geometry. You will see later that there are ways that we can improve the geometry that we've created at the beginning. Okay, and this is just a summary of the molecule that we have given to Orca to run calculations on various different coordinates, units. It tells you the basic set that we've used to run the calculation. So the basic set, we then how the basic set is actually interpreted by the program. All right. And if you scroll down, you should see your results coming up. So this is the main Hadley-Fock calculation. You will see that. So it says SCF here. So you heard from Alex, and the Fock is also known as a self-consistent field method. So self-consistent field is abbreviated as SCF, right? So it's a self-consistent field method. So you need to solve for the Hadley-Fock equation iterations after iteration after iteration until you reach convergence. So this is where you've got to convergence. It tells you that sort of wait for that to scroll down. It's going to show something. And after the calculation is converged, the output file will tell you a summary of the energies that have been produced by the calculation. The total energy here gives you the total energy of the Hadley-Fock wave function that you have just calculated. Now, this total energy is made up of many different components. So you've also remembered from Alex's lecture this morning that in your Hadley-Fock calculation, you've got some kinetic energy, some external potential energy due to the interaction between the electron and the nuclei, and you've also got the Coulomb energy, which is like and sometimes it is quite useful to look at these different components of the energy to find out what your state actually means. But for today, we are only interested in the total energy. We don't really want to care too much about these values down there. It's okay. Yeah, I'm trying it again, but if we can connect this straight away to the projector, it might be better. Yeah.
All right. Then I was thinking to keep on continuing.
Yeah.
So I'll let them know that after this session they could go back to our social media platform and rewatch.
But sometimes it's not recorded.
It's not recorded.
Yeah, because I'm not connected to the internet, so that's the problem. But I'm going to share all the files anyway, so maybe that's fine. But
So maybe it's better to let them know so that those who are anxious,
yeah,
etc.
because there's remote viewers that need to be able to access this as well. And if we just do that through the projector, they can't see that. So I think it's fine. Just something like this. No. It's, yeah. So essentially what I'm trying to say here is, well, the output file will probably come up at some point, but once you've run the calculation, you will get an output file that contains a lot of information. At first, it might be very overwhelming to just look through these files because there's so many lines of text that you've got to read and you don't really know what you're looking for. But once you are familiar with the calculation, once you've looked through one or two output files, you will start to see that the information comes in different patterns. And let's say you're running a happy fault calculation, there will be certain key information that will be available through the output file, and you will extract what you need to extract from that. Right, okay, so we are back to here. Maybe these points are good for the participants to sort of catch up as well, hopefully. Okay, so this is task, I believe it's task 3.1 in your handout. So this is to run a simple Hartree fault calculation.
What we'll try to do.
Okay, so, right, so I think we are at the point where we've run our fast calculation, which is a very simple Happy-Fock calculation. I know it's been a challenge because, getting technology to work is quite difficult. But what we think we're going to do is we'll try to go through a few more calculations. We'll let people break for lunch as well, and then maybe during lunch, you can try to do something on your own. But what we'll do is that after this, when I get back home, I will record the video of me actually going through all these tasks, and then we'll upload this video online somewhere, and then I can ask Aodi to share this to all the participants, so you can actually watch through the tutorial. I will probably try to explain the way I would here, but then it's going to be with better sound and better recording of everything, so you can actually see what's going on, and then you can maybe follow them and actually try to go through the task. Would that be agreeable? Most people can. Yeah, so I think now is probably a good time to break for lunch. I don't know if lunch is here yet. If not, we can carry on for a bit more, and then when lunch is here, we can stop. But if lunch is here, then let's eat. But maybe lunch is not here yet, so let's carry on for a bit more. Okay, so once you've run the calculation, you get an output file. I've talked about that. You will get a lot of information in the output file. They will tell you all sorts of things about the calculation you've run, like the SCF energy, how the SCF conversion was actually reached. What sort of other information? We know that in Happy-Fock, we have orbitals, right? So you've heard from Alex that Happy-Fock theory is a single determinant theory. The Happy-Fock wave function is a single Slater determinant, and the Slater determinant is constructed from a set of molecular orbitals. So it makes sense to talk about molecular orbitals in Happy-Fock theory. So in the output file that you've got here, of course, because it's Happy-Fock theory, you'll get access to all information about molecular orbitals, the molecular orbitals that construct the Happy-Fock wave function that we have just obtained. Right, so what it tells you here is the energies of these orbitals. We've said before that this molecule has got 16 electrons. And because we are running a restricted calculation, every molecular is doubly occupied. And that is shown here. This up here shows you the occupation number of the molecular orbital. This molecular orbital is occupied by 2 electrons. This one is occupied by 2 electrons, and so on and so on. And you've got 8 molecular orbitals in total. So overall, you've got 16 electrons, which is exactly what you've told Orca to run the calculation on. This is for neutral formaldehyde, which has 16 electrons, and you should expect to see 16 electrons here. The orbital energies are arranged in increasing order. So this is the lowest occupied molecular orbital. This is a very core-like orbital. It's very low in energy. It's deeply buried in the molecule. It's unlikely to participate in any chemical reactions. But when you get to the highest occupied molecular orbital, this will probably be the molecular orbital that is involved in chemical calculations, in chemical reactions. So these orbitals here are what we call frontier molecular orbitals, the molecular orbitals that are sort of near the homo-lunar gap, essentially, right? So that's your HOMO, that's the highest occupied molecular orbital. This is the LUMO, which is the lowest unoccupied molecular orbital. And usually these orbitals are important for chemistry. And we will look at ways to visualize these orbitals later using IQ1. Further down, you also have more information like molecule population analysis, which tells you where the charges are in the molecule, which tells you, for example, on carbon, you've got a slightly positive charge. On oxygen, you've got a slightly negative charge. And that makes sense because you would expect oxygen to, hold on to this by electronegative. And so on. And of course, the sum of the charges in the molecule must be 0 because the molecule is neutral. And you've got a lot of information you can get from output files. Alright. Okay, so that was task 3.1, essentially. That's just to run restricted Hadley-Fock calculation. And from this calculation, you can extract a lot of things. Okay. But of course, Hadley-Fock is very simple. So you don't just do Hadley-Fock in chemistry, because you know that Hadley-Fock is a very simple theory, and it's unlikely to give you anything that is chemically meaningful, because the Hadley-Fock approximation misses out a lot of electron correlation. That means it doesn't take into account how electrons sort of interact with each other and treats electrons as independent particles in the mean field. So that's not very good. So we want to improve on that. So there are other types of calculations we can do. But before we do that, we need to look at how basis sets affect your calculation. You've heard earlier that the choice of basis set is like the choice of the Lego blocks that you use to build your quantum chemical quantities. And you need to pick an appropriate set of Lego blocks essentially to describe the system properly. And that is essentially saying that you've got to pick a set of you've got to pick the right basis set to do your calculation then. And how do we know which basis set is right? The way we know that is to run something called a basis set convergence calculation. A basis set convergence calculation is essentially one where you run the same calculation but in different basis sets. Right, so you repeat the same calculation but in increasingly larger basis sets. So you've got 631 G star. You then run that in a larger basis set, which is 631 G star star. So there are two stars now. That means you've got two sets of polarization functions. And then you change to something else, which is called CCPVDZ. Don't worry too much about the names of these basis sets, but the further you go down the list, the larger the basis set. And you would expect that the larger the basis set, the better the calculation would be. And that is in general true. But of course, the larger the basis set, the more expensive the calculation is going to become as well. I mean, imagine trying to build a castle with a lot of Lego blocks. That's going to take you a long time, rather than trying to build just a small house with fewer pieces of Lego blocks, right? But the more Lego blocks you have, the more impressive the structure you can build. And that means that the larger the basis set, the more accurate the calculation is going to become. So this task here, this is essentially what you would do in your free time. If you are really bored, you don't have anything else to do, run the same calculation in a variety of basic sets and then compare how the results behave. So I've already done that, so I can actually show you the graph of the Hadley-Fock energy for neutral formaldehyde in a variety of basis sets. Let me see if I can get that to work. So don't worry too much about the orange line. If you focus only on the blue line, the blue curve here gives you the Hadley-Fock energy that I've computed in a variety of basis sets. And you can see that these numbers here on the x-axis gives you the number of basis functions in the basis set. And as you can see that the larger the basis set, the lower the Hadley-Fock energy that we are going to get. And at around CCPV5 set, you can see that the curve has sort of leveled out. So that is probably quite safe to say that you've reached some sort of basis set convergence there. Essentially, this is saying that as you go down, as you increase the size of the basis set, the Hadley-Fock energy becomes lower. And we know from variational theorem that for the ground state energy, the lower the Hadley-Fock energy, the better the description of the ground state. So the lower the better for this one here. So you see that this curve is sort of approaching a minimum at around minus 113.92 atomic units for energy. Right? So this is how a typical basis set convergence calculation curve would look like. You will see something like this. This is the trend in the calculation. It shows you that if you've picked a very small basis set, you see that that is a huge error gap. That is a huge gap from where the true energy is supposed to be, right? So you've got to do your calculation in
in a variety of basic sets to actually see how it behaves when you change the size of the basic sets that you're using to describe the system. Okay, so that's basic set convergence. It will probably take you some time to run these calculations because essentially you've got to repeat the same thing over and over again. So I wouldn't advise you to do this here because it's going to take quite some time. But once you are experienced with calculations, instead of doing that manually, you can write scripts that actually cycle through all these basic sets and run them automatically for you. So you don't have to do this one by one manually. Right? But maybe when you first start out, you can just go through it step by step to actually get used to the calculations first before you automate the process. Right. And of course, you can do the same thing for the anionic form of formaldehyde. This is another system we will consider throughout the workshop. It's the anion form of That's smaller because it's in the smaller basis set, but it should be significantly better. So actually, if we compare the same basis set, I'm going to do that like this. Actually, it might be easier. Yeah. They're virtually the same. Yeah. Okay, so don't worry too much about these comparisons. Let's move on because I think time is running out. Because I think lunch is in about 15 minutes. So there are many calculations you can run. So once you've set up an input file, once you've run your first calculation, subsequent calculations are a lot easier to do because you can just modify the input file and make it different for the different calculations that you're running. And you can also do DFT calculations. Input files are basically the same. You just change the method to DFT, and then you should get numbers. Right? So that's just doing a lot of ground state calculations. But the question is, how do we actually know what these states look like? Right? What do we do to actually understand the states? So one thing we can do is to visualize molecular orbitals. Once you've run a Hartree-Fock calculation or a DFT calculation, you can look at molecular orbitals because molecular orbitals allow you to visualize what the state looks like, what the Hartree-Fock wave function looks like. So I think I might just show some orbitals I've obtained earlier. The way to do that is, if you want to obtain orbitals, you just add another section to the input file. It's quite simple. So it's basically just tell Orca that, okay, run my calculation in Hartree-Fock and also plot these orbitals. So you just add a few more lines to the input file to tell Orca to do that. So the files that you will get out of that would be a bunch of, what task is it actually? This is 4.1. So if I go to 4.1, let's look at the neutral orbitals, for example. You will see that Orca will produce a bunch of cube files, and these cube files are things that you can open in an IQ mode to actually see the forms of the orbitals. So, for example, we've known earlier that orbital 7, so that's actually the 8th orbital, is the HOMO in the neutral species. So let's have a look at the HOMO to see what it looks like. So I'm going to open that file with IQ mode. Right, so let's look at the orbital of this, let's look at the form of the 7th molecular orbital. So to do that in IQ mode, you sort of just go there, go to cube data, run that. And that is your HOMO, right? What does that HOMO look like to you? So I'll make it a bit easier for you to visualize. Give me a second. So this is the highest occupied molecular orbital in formaldehyde. Okay, I've been told to wrap up, so I'm just going to finish this. I'll show you some orbitals, and I think we're going to call it a day. I didn't manage to show you everything, but I promise that there will be videos on YouTube. I'm going to do that later, so you can actually, I'm going to walk you through all of these tasks in a much more detailed way without any of the technical hiccups, so we can actually, get through them. Anyway, so just to answer my question, this is the non-bonding lone pair on oxygen, right? This is it looks like a pi star orbital, but it's not. This orbital describes the non-bonding lone pairs on oxygen, and this is how that actually looks in reality. Yeah, you've got the two lobes here that gives you the lone pair behavior, essentially. It's just non-bonding. If you look at the one orbital below that, so that's going to be A6. Just quickly to compare, you will see that this orbital here is actually the C10 pi orbital. That looks like that. All right. So you can do these very simple calculations to get pictures of molecular orbitals that you might have heard of in, maybe a course in quantum chemistry or in inorganic chemistry, but you want to actually see how the orbitals look like. So these calculations allow you to do that. Okay, so I think with that, I might probably wrap up because we don't really have time to get through everything else, but I promise that I'll make the materials available online for you to watch later. Okay, so there's a lot more that you can do, for state visualization, for excited state calculation, and for equilibrium geometry. So you'll be able to do that. All of the materials is in the handout that you have been given. So if you look at that first, and then I'm going to try to do the videos that actually walk you through the task as well. Hopefully that will be helpful. But I think for now, I'm just going to give the floor back, and I think it's time to break for lunch. So thank you very much.
Thank you. Please put your hands together for Dr. Wang. That was a PhD masterclass. My brain is still trying to recover. I'm still having smoke coming out from several places. I hope we learned something. All right, so it's lunchtime. That's the one we want to hear now. Lunchtime, blessing time. So we're going to if you left your seat to go to anywhere to do anything, please go back to your table because they are going to share it table by table. They have 4 persons for a table. So please go back to your table. I think we are done with the computation for now. Go back to your tables, please. Go back to your tables so they can attend to you table by table. I'm seeing tables that are like 6, 7 persons. That's not supposed to be. So please, let's decongest this table. Those that are originally here, stay. If you are not here, please move to your table. Can we decongest this table? Move to your table. If you were not originally here, please move to your table. So it can make it easier for those sharing, please. Thank you. So we'll have lunch now, and in an hour, you.